that, I will go ahead and turn it over to Sven.
Thank you, Kelly, for the introduction. I am Sven, and together with me, Sebastian, we will talk about the parameters regarding inductors. And starting with the agenda, there are so many questions regarding inductors. So we will have this webinar in two sections. The first section, it's going to bring the technical aspect or the background regarding inductors, some definitions, some stuff regarding electromagnetism, some basics. This information will help you to understand the second part, which is going to be more practical, to understand how the currents are, the rated saturation current, resonance frequency, some layout, guidance, and ending with some MPS inductors overview and showing you some performance regarding inductors. And of course, at the end, we will discuss the questions you have. Don't forget to type them in the chat. And starting with this, let's go through the main questions you probably have when starting to select an inductor, because the market is it's huge. So there are so many kind of inductors, so many shapes, and it's not really easy to select or to filter the right one. So what is the inductor I need? It's depending of the physical aspects. So do I need some shielding? It's unshielded. I need low profile, molded, high current. And there are so always some electrical parameters that is important to know. What efficiency do I need? What current is necessary? Do I need more rated or saturation current? EMC aspects, what application, sizes, and so on. So there are so many questions, and we hope with this webinar, we will try to clarify some of them or mostly of them. And let's start with the definition about inductors. And an inductor, it's a very simple component. Inductor is just you just need two components or one component. Second component is optional, but you have advantages of it. The first one is the wire, and the second is the core material. So the core material, we have some advantages when we use a core material. We will discuss this later. But an inductor is nothing else than a wire wounded in a coil shape. That's it. And why are inductors so special, actually? Inductors have a very special property, and it's that opposes a change in current in relation of time. That's the main property of the inductors. So when the current in the circuit is trying to change, in that moment is when the inductor is actually starting to work. So it opposes a change in current from a circuit. If a current is going in this direction, so it's going left to the right, and if it's increasing, the current is increasing. So inductors will try to keep them from increasing. So it's going to have a potential in the opposite direction. If current is decreasing in the circuit, so it's going in this direction or decreasing, inductors will try to keep them from decreasing, so they will set up a current in the same direction. We will have only a potential difference in the inductor if the current is changing. So if the current is constant, there will be no potential difference in the inductor. And the formula defines how much voltage, or how is the voltage potential in the inductor if the current is changing. So the inductor have inductance, so how much inductance is changing in relation with the change of current in time. But what is the function of the inductor? So, and the main function of the inductor is to store induced electric energy and magnetic energy. That's the main job of an inductor. And this is when we have a current flow through the inductor in the wire, flowing through the wire, a magnetic field is generated and an electromotive force in opposite direction it's created. And that describes the formula, describes that there is a minus, and this is because the electromotive force is in the opposite direction of the actually current flow. Inductance of an inductor opposes the change of current in time. But what is the inductance? So the inductance are the units, or it's the parameter from the inductors, and the units and it's measured in Henry. So the units from inductance is Henry, and inductor have inductance. An inductor, we have several the parameters for inductors. We have the permeability itself from the core material we're using. So the constant of nature, which is the vacuum constant, so from free space, this is close to 1. And the relative permeability, it's depending of the core material we're using. Core material we will discuss in a few slides. We have also the dimensions of the geometry of the core. We have the cross-sectional area, and we have the length of the core. And the second component is the wire, so we will have certain amount of turns in the component. As you can see, mostly of the parameters are related or are having a very good high impact in the inductance of an inductor and the wire material and the number of turns. But what can we do to increase the inductance, or what are the parameters the production or the manufacturer it's able to do some special or higher inductance values? There are certain kind of core materials. These core materials have high permeability values. Some of them are medium, small, or high amount of units for permeability, and increasing or having high permeability core material will increase also the inductance value. These have also some advantages regarding core materials. Discussing them in the next slide. Then we can reduce the length of the core, but if we reduce the length of the core, we will not be able to have enough, or we will reduce also the amount of number of turns. So this is going to be reducing the length will increase the inductance, but decreasing the number of turns will decrease actually. So it's always try to find a balance how the production is going to do that. Then increasing the cross-sectional area will increase the maximal inductance value, but also will increase the dimensions, so the size. And having more size will have more weight. That's something we don't want. And the other option is to increase the number of turns. But if we increase the number of turns, what we will have more resistance, and this is also something we maybe don't have. So at the end, what we need is to have a balance between all of these components. It's a trade-off to get the best size, the best weight, and the best possible performance. So there is no perfect inductor, but there is a balance of all these parameters is what is making a good inductor. So the smallest packages, it's what is the target, so to reduce the weight. And also we don't want to have higher resistance. So we need to try to find a way to have less turns as possible in an inductor for that. Permeability. This is regarding core materials. What is permeability? It's ferromagnetic materials have an ability to respond when a magnetic field is going through. And this ability, or how good is this magnetization of a component, is given by the permeability. This is how much magnetic flux can concentrate a core material, our core from an inductor. Having a core material, we have also some advantages. We'll have, as discussed already, for permeability, the magnetic point of view is to concentrate the magnetic flux. So when we have more magnetic flux, we will have also more saturation current. The function benefit of having a core material is to store energy and use it in the system as needed. And from the mechanical point of view is to have a body to wind the turns of an inductor. The permeability or the core material, it's dependent of the material we're using. So there are several materials, the frequency, temperature, current, and pressure. When we increase the permeability, we will increase the inductance value itself from the inductor, but the resonance frequency point will be less. So it's going to drop earlier. It's not so critical, but it's something you need to know, that the resonance frequency point is shifting to the left. So we have several kind of core materials that are used for inductors. When current is going through the wire, a magnetic field is generated. This magnetic field in both cases is same. Just the magnetic flux concentration within the core, it's higher when we have a core material, so a high permeability core material. In the case of the air, so this is a non-magnetic material, so we will have here a permeability from 1. In the case of the ferromagnetic materials, we have several components, so iron-based inductors, nickel zinc, manganese zinc, and some mix of alloys. For example, the iron-based components are known, so the ferrites or the molded inductors. When we use powder, ferrite, iron powder material, this is going to have 50 to 150 units. And as you can see, the permeability is giving a good idea how much or how high could be the inductance value. As you see, it's the lowest from all of 3. So the inductance value is limited in this case. Nickel zinc, manganese zinc are mostly of the drum core inductors, are based on this material. They have higher permeability values, so you will have also higher inductance values. Every component or every core material we have will have also some advantage, let's say, regarding of the thermal performance, regarding of efficiency, regarding of what frequency we're using. So there is not a perfect core material, but there are also advantages from using different core material for inductors. And we need to discuss also some losses, as we have 2 kinds of components to build an inductor. We have the wire and we have the core material. So we will have wire, in this case is copper losses, and we will have, regarding core, the core losses. When we compare the complete losses in a system or for inductors, when measuring the complete losses, you need to pay attention when you have several alternatives. They may, at first instance, from datasheet, they look very similar. Maybe it's the same size, same RDC value, very similar currents, but at the end, when measuring and making comparison on efficiency, it may be some differences. And this is regarding the whole component, so the copper losses and the core losses. Copper losses, the wire or the copper have certain resistance, and this conductivity loss will be reflected on the heat dissipation of the wire. We have also the AC losses. This is driven by the frequency and depends of the winding structure. We have here two effects, the proximity effect and the skin effect. And we have the core losses. So the core losses are magnetic material loss. This is caused by the eddy current losses and the hysteresis loss. Regarding the copper loss, it's the heat dissipation in the system. So the higher RDC we have, the higher heat is dissipated, the higher power loss we will have, and the efficiency will be less. It will be reduced. At the end, what you see in the data sheet, it's or should be in the best cases the best winding method for an inductor. So this will be performed on the less RDC. You will have the lowest RDC by having a very good winding method, but also you can reduce the RDC having less turns, and you can do this when you have a high permeability core material. So more permeability, then you will be able to reduce the number of turns. Then we have the effects caused by the eddy currents when AC current is flowing to a wire. So magnetic field is generated, inducing these eddy currents. The eddy currents are dependent on the frequency. So the higher the frequency, the higher AC losses we will have. When we talk about proximity effect, these AC losses are more generated in two ways, in a non-uniform way. When we have currents flowing through the wire, and we have several layers of the windings of the inductor close to each other, the nearby winding will affect the nearby layer. When current is in opposite direction, the current concentration will be more on the side close to the next wire. And when the current is flowing in the same direction, the concentration will be further from the wires. When we talk regarding the skin effect, it's the tendency to flow the current to the outer side of the wire. So the higher the frequency, the thinner this skin effect will be. And at the end, you are reducing the maximal cross-sectional area where current can flow, and reducing this cross-sectional area will increase the AC losses. And this is dependent from the frequency. It's very dependent from the frequency. So the higher the frequency we have, the higher the PAC will be. Then coming back to the DC losses, the copper losses, there are some tricks to get higher or better resistance or lower resistance. And this is when we use the wire. So this is mostly used from copper. We have copper, we have the resistivity of the copper material itself, and we have the geometry. The shape of the wire. So we have two options here. We have the round wire and the flat wire. And the only one thing it's changing from these two geometries is the cross-sectional area. The cross-sectional area A, which is reflected in that way when we imagine we have the same length and the same height, so same length, same diameter, same height, one by one. We see that the flat wire will have higher cross-sectional area. And when we have higher cross-sectional area, we will have automatically less resistance. And less resistance means less PDC or copper loss, right? But not everything is advantage or disadvantage for round wire. Round wire There are some characteristics. As you see, the cross-sectional area it's less. So you will be able to have higher inductance values, and this is because you will have more space to add more turns. But in the same way, adding more turns will increase the resistance. So you will have more copper, so more resistance, and the current will be reflected also. So you will have lower IDC. When we talk regarding the flat wire, the cross-sectional area is bigger, so we will have we will need more space to add the turns. So this space is limited by the physical geometry of the flat wire. You will, or we will be able to wind more effective, to use this winding window more effective, and so we will have less turns in general. Less turns will be less copper, so less RDC, less losses, and we will be able to have more possible current. And at the end, when we look for high performance or to squish the last efficiency percent from a system, so what we want is to reduce the most possible RDC to get the highest efficiency, and we don't want to have heat, so we will reduce in that way also or have better thermal dissipation in the system. And we have also core losses. So this is regarding magnetic material loss. This hysteresis loss, this is a state dependent of the magnetic flux and the magnetic field. And as we remember, permeability is how could a material interact when we apply a magnetic force. This chart describes how the magnetization process of the ferromagnetic materials are. In general, the ferromagnetic materials, they have a certain structure, this atom structure, also called the domain. And the single domain structure, it's divided in some magnetic walls or separate to these magnetic walls. Each magnetic wall have a magnetic domain, and in the domains there are some domain orientation. So the domain position, it's at first instance is random. So this magnetic moment is random. There is no specific direction when no magnetic field is applied. So knowing this structure, when we go from the initial curve, so the saturation process or steps from 0 to 3, when we don't have any magnetic field applied in the system, so the whole magnetic moments are oriented at any direction, there is no specific direction, and then we start to increase the magnetic field. So every magnetic moment will try to align to the same direction of this magnetic field. So they will try to point to the same direction, to the right in this case. And with increasing magnetic field, they will turn more and more on that direction. And in the case, and the core losses is when this crystal structure, this magnetic moment gets stuck in the structure, and when they finally succeed and break the structure and finally point to the right direction, at this moment is when these core losses is happening. So the thermal, and they are dissipating some heat also for the losses, for the hysteresis loss. And when we reach the final state, the state 3, we say that the inductor cannot concentrate, or we cannot apply more flux density. So the inductor is fully saturated already. And let's say we say that's the maximum saturation possible for an inductor, and we reach the saturation state. Exactly. Okay, and now let's go further with the practical part. Sebastian will continue the webinar, and you can take over.
Thank you very much, Sven, and hello, everybody. I'm going to continue now with the more practical part, starting with the rated current. So the rated current is sometimes also called the temperature rise current, and it is mainly the DC current that causes a certain self-heating due to the RDC of the winding. Unfortunately, the definition of the rated current is not standardized. So when you're looking at different data sheets, you will figure out the different definition may vary from manufacturer to manufacturer. When you calculate the temperature of the inductor, the equation should be T-op equals T-amp plus delta T. T-amp is the ambient temperature given by your application, and as an example, -40 to +85 degrees C. The rated current is related to a certain delta T, which is the temperature rise due to the self-heating of the inductor and can be found in the data sheets as well. 20, 30, or 40 Kelvin in temperature rise are quite common, but there also might be exotic ratings as well. Please always take care of the footnotes in the data sheets to compare apples with apples. The operating temperature, T-op, is given as a maximum value in the inductor data sheets as well. And please don't exceed this maximum operating temperature. If your ambient temperature is getting higher, you should use another inductor with a lower self-heating at your rated current. And this can be easily achieved by choosing a larger package size. Next, please. So the self-heating of an inductor is mainly the DC losses in the form of temperature. So as Sven mentioned already, the DC losses is calculated with IDC squared times RDC. That's why the self-heating characteristics is exponential, as you can see in this slide. In this particular example, the rated current of around 23 amps is causing a temperature rise of 40 Kelvin. And considering your ambient temperature, this temperature rise may not exceed the maximum operating temperature. The such temperature rise characteristics is shown in almost every data sheet, so you can easily figure out which self-heating is expected at which DC current. Next, please. The second important current-related parameter is the saturation current. In the picture on the top right side, you can see the initial state of a ferromagnetic core, where all the magnetic domains are oriented randomly. When current passes through the coil, it generates a magnetic field and the magnetic domains start to align according to it. On the right bottom side, you can see the full saturation state when the magnetic core is completely magnetized. So all the domains are aligned and become consistent with the magnetic field. This means the higher the magnetic field H, the higher also the magnetic flux density B. And the saturation level is determined by the air gap. Next, please. On this slide, you can see the comparison of well-known inductor types and their saturation level rating. So the first one is the drum core type with a ring shielding, where the open side is covered by a ferromagnetic ring that acts as a shielding against radiation. Due to the small air gap of this construction, this type has the lowest saturation level. Followed by the semi-shielded type, which is basically an unshielded drum core type, but the winding is completely covered in a mixture of resin and ferromagnetic powder. This way, a shielding effect is achieved, resulting in a low to medium saturation characteristics. Coming to the most basic inductor type, which is the drum core inductor without any shielding, that can reach a medium saturation level. Last but not least, we got the molded type in the round and the flat wire construction. So the structure is an air coil and the core is molded around the coil. Due to the used material, the air gap is distributed over the whole core. That way, the highest saturation level can be achieved. So the saturation current point extends when the air gap is getting increased, and molded inductors have a distributed air gap all over their core. Next, please. So how does the saturation now impact the inductor's behavior? The more current applied, the more the inductance drops. The red curve shows the hard saturation behavior of a ferrite drum core inductor with a steep drop, while the blue curve shows the soft and flat saturation behavior of a molded inductor. Comparing the two curves, the drum core inductor reaches the 20 and 30% drop at the lower current than the molded one. As you can see, the ripple current margin between 20 and 30% of inductance drop is bigger when using a molded inductor, providing you more flexibility in your applications. Please be aware that also the saturation current definition is not standardized, and there might be different specifications between 10 up to 40% of inductance drop. All MPS inductors are rated with a 30% drop, for instance. So please read the footnotes carefully, not to compare apples with oranges. A smaller inductance value or a larger package size allows the inductor to handle higher saturation currents, though also dissipates more heat. Next, please. Sven mentioned already that the inductance value is directly related to the relative permeability, which is temperature dependent. Ferrite drum cores have a comparable high relative permeability. That is why these inductors saturate earlier the higher the operating temperature gets. This causes challenges for wide temperature range operation. The composite molded types instead, on the right-hand side, have a low relative permeability core, showing a narrow deviation between the 25 and the 100 degree C curve. So in case a stable temperature behavior is necessary, the molded types are the way to go. Next, please. Another important parameter is the self-resonance frequency. The self-resonance frequency, SRF, is the frequency at which the parasitic capacitance of the inductor resonates with the ideal inductance, which results in a very high impedance, as you can see on the right side. At this frequency, the inductor looks like an open circuit. Exceeding the SRF, the inductor will just work as a capacitor. So the self-resonance frequency is strongly depending on the relative permeability of the core material. So the higher the permeability, the lower the SRF. Air coils without a ferromagnetic core show the highest self-resonance frequency. Therefore, they are perfect for high frequency applications. When designing a DC-DC stage, please keep in mind to use an inductor with a much higher SRF than your switching frequency. Next, please. Coming to an underestimated topic, which is the start of the winding. When designing a DC-DC stage, you want to place the converter switch node close to the start of the inductor's winding. Inductors don't have a polarity, as for an example, capacitors do. So why is the start of the winding important? The first layer of the winding, which is the inner one, gets shielded by the following layers. So by keeping the start of the winding close to the switching node, audible noise from harmonics and inductor cost emissions can be reduced by around 3 to 5 dB. In the product picture, you can see the small dot on the top side of the inductor, which is indicating the start of the winding. There is other manufacturers not controlling the start of the winding position and just indicating such a dot or a bar for absolutely no value. As a high quality supplier, MPS takes care that all products show the start of the winding in the correct way. Please always take care to place the start of the winding close to the converter switch nodes. Next, please. So which kind of inductors does MPS provide? There is 3 different types of molded inductors. So the Mpl-A-T is the smallest series, available in 3 different sizes from 2010 to 2514. For the optimum placement on the PCB, the start of the winding is indicated with a dot as shown in the picture on the right-hand side. It is a low profile series with maximum height of 1.4 millimeters, offering all the benefits of a molded inductor, which are low DCR, a high saturation current capability, and a soft saturation behavior, which is stable over temperatures up to 125 degrees C. So if height and PCB space is restricted in your application, the Mpl-A-T is your choice. Next, please. The second molded series is the Mpl-A-Y Series, which is a round wire molded series, also offering benefits as a low DCR, high saturation current capability with a temperature stable soft saturation behavior. The size spectrum is starting from 3020 with a maximum operating temperature of 125 degrees C to 1265 up to 155 degrees C. The wide size range makes it the all-rounder, able to cover many different applications. Next, please. Number 3 is the Mpl-A-L. Unlike the other series, this series is built up with a flat wire winding. We've learned today the use of flat wire can lower the DCR and thus reduce the DC losses. This makes the Mpl-A-L series highly efficient and perfect for high performance applications. On top, the AL series has all the benefits of a molded inductor as well, and has the high current capability, the soft saturation with the stable temperature characteristics up to 155 degrees C. And for sure, the famous start of the winding indication as shown on the picture. MPS offers the Mpl-A-L in 5 different packages from 4020 to 6060. Next, please. Last but not least, we have the Mpls E-Series, which is a semi-shielded one. This means a mixture of epoxy resin with ferromagnetic powder covers the winding to magnetically shield the inductor. Due to the structure, the series is optimally suited for cost-optimized designs. It shows a low DCR and a high current capability with a maximum operating temperature up to 125 degrees C. The Mpls E is available in 4 different sizes from 2512 up to 6040. Next, please. Okay, so let me pass the word to Sven for the efficiency.
Thank you, Sebastian. Let's continue with discussing what is going on efficiency. When we talk the overall package regarding copper loss and core material loss, and this is what we did in this case, in this measurement, in this chart. So this chart is just describing the overall efficiency when using a component with same characteristics, same electrical characteristics. We see that the resistance, we have very similar resistance, plus minus 5%. So it's really very similar. And when we compare the shape or the appearance of the inductor on the right side, we see here the MPS component, and on the left side, we see the component without from the top vendors in the market. The one difference I noted immediately in this case is the starter winding. MPS is having the starter winding on the inductor, and the and the random vendor in the internet is not having this indication. So this start of winding is really a good kind of helps to increase the performance from your device, from your system. And we start to do this comparison efficiency with the MPS IC MPQ8883. And we did this firstly at 500 kilohertz. We are comparing right now 10 microhenry inductor with 3 different inductors from the market. Same size, same shape, same characteristics, or very similar characteristics. So it's alternative 1-to-1. And when we see the comparison efficiency measurement results, we see the blue curve. The blue curve is the MPS inductor. We see that MPS is having overall a very good performance, or even higher. So it's even showing 1 or 2% more or higher efficiency than the top vendors in the market. And this is just describing that MPS is having a very good quality components as well. Because 1 or 2%, it's really making a big, it's not much, but it's making a big difference when it's when we are talking from overall efficiency from the system. We have this measurement at 500 kilohertz, and we discussed that every core material, or the core material, will behave different at different frequencies. Just to show you this, we have a second measurement. The second measurement, or the first measurement at 500 kilohertz, is above 96.5 at 1 ampere efficiency. And when we increase to 1 megahertz, we see that at 1 ampere, we will have more or less 96% efficiency. So you see it's decreasing by increasing the frequency, but still MPS inductor is performing very well, showing even at higher frequency better performance like in the competition. We will have at the beginning as a constant losses. This is when we are starting the measurement. Then we have the switching losses. It's more related to the core losses. And then at the end, we have the copper losses. And again, this is having the same shape, same kind of component. And these are the real results without having any, with the same board, with the same component. And now a summary from the topics we discussed today. The main, an inductor in general is an inductor reacts to the change of currents. The function of an inductor is to store the induced electric energy as magnetic energy. And it depends, the inductance value depends from the core material what we are using and the number of turns. From the magnetically point of view, when we use a core material, we can intensify this concentration of magnetic flux. So this density will be much higher when we have a high permeability core material. More magnetic flux, more saturation current. We discussed also about losses, core losses, copper losses, the currents, rated and saturation current, some layout recommendations. And I would like to mention also that MPS is having a very high efficiency components, as you saw in the results, with the really top, with the best inductors you can see in the market. We have also reference design. So MPS is having evaluation boards using MPS ICs. And we have reference designs, including the MPS inductors on this board. So these reference designs are available in the website. And we have for every MPS inductor, we are able to have an MPS inductor selected. We have meaning we have a wide range of inductance values that are matching with the MPS inductors as well. And we have also an inductor calculator tool, which is in the website. And when you are selecting the IC and you know your specifications, your converter specifications, what are the inputs, the outputs, what frequency, what ripple current, you just need to put this information in the inductor calculator tool, and this will filter according to this selection. And also, I have to mention that MPS inductors have right now lead time from about 20 weeks. And now Sebastian will take over regarding the summary of CODICO.
Thanks, Sven. Yeah, just a few facts about who we are and what we're doing. So CODICO stands for the Component Designing Company, and we are a design-in distributor for high-quality active passive components and interconnect products. We're in a close cooperation with MPS since 2008. And besides all the benefits of a distributor, we are also offering certain support benefits, which is, as an example, as part selection according to your design specifications, sample and eval boards with a quite short lead time, schematic and layout design proposals, layout and PCB reviews, troubleshooting, and for sure, competitive pricing and logistic services. This kind of support is done by our FEs. They're working in two different labs. One is in Munich in Germany, and the other one is in our headquarters in Pertelsdorf, close to Vienna in Austria. So let me pass the word now to Kelly and jump into the Q&A section.
Great, thanks guys, a lot of good information today. I do see that we have multiple questions that have come in. So once again, if you haven't noticed, you can mouse over the QA icon at the bottom of the Zoom webinar interface and type in your questions. We do have 11 there. And then I do want to emphasize this session is being recorded and will be available on demand within the next couple of days here. We will send out an email that has a link to both the presentation and the on-demand video. And you can always check for our past webinars at monolithicpower.com/webinars. All right, so let's jump into the question. So the first one came in, I think when you were going through core loss then, and that question was, which losses dominate inductor losses, DCR or ACR?
Okay, regarding losses.
I think it was actually back like on the hysteresis losses, maybe one slide before this.
Well,
Two slides.
The series losses. Well, I think it's related to the DCR, ACR. Okay, I think it's actually more related to what are higher, the copper losses. The copper losses are two kinds of losses. We have the DC losses and the AC losses. DC losses are the more dominating part of the copper losses. And then we have the magnetic losses regarding the core material, and they are also dominating. The hysteresis loss is also a big part of the losses. That's why, and this is something you don't see when you buy an inductor in the datasheet. You don't see the hysteresis loss. This is something we cannot read in the datasheet. That's why I say it's always important to have this kind of measurement comparison, and there is where you see, okay, how is the real efficiency of the inductor.
Great, thanks. And then the next question I think came in while Sebastian was doing his first slide. And that question is rated current the saturated current?
these are different. So let's start with rated current. Rated current is regarding the temperature of the inductor. So it's the self-heating of the inductor itself. And this is caused by the wire. The self-heating, it's given in the datasheet as rated current. There is a certain rated current in the datasheet, and normally you see at what self-heating level. We are giving this at MPS by 40K, and this is the way you can read it. So we have this 40K temperature rise. This is the self-heating of the component. And that's the point where you can read the rated current in this case regarding rated current. This is self-heating of the wire, of the inductor, by a certain amount of current. And then we have the saturation current. Saturation current is more related of the inductance drop. So this is more related to the core material, magnetization of the core material. So how is the inductance drop at given percent? So we have a rated saturation current from example, in this case, 8 amperes. At 8 amperes, we will have inductance drop from 20%. When we see here 100% is 1 microhenry. So 20% is 0.8. And this is the way to describe there are different currents. This is more related to inductance drop. At 8 amperes, you will have 0.8 microhenry.
Okay, and the next one is where do monolithic inductors saturate compared to wound inductors?
We have different kind of construction types at MPS. We have the semi-shielded type, and we have the molded, type. So the saturation level, it will be regarding semi-shielded, as we have some epoxy mix covering the wires. This means we will have we were increasing a little bit the permeability because we have additional core material here. So the saturation level will be a little bit higher than the typically drum core with shielding or without shielding. So this is regarding the air gap. Here, as you can see, when you have a shielding ring, the air gap is very less. So we have very small air gap on the inductor, and as we are getting unshielded, the air gap is going to be bigger, and also the saturation level. When we have a molded type, we see that we have an air coil pressed with powder material and forming an inductor. This is the molded inductor. So we will have the best use of the component without empty spaces, as you see here. So there is no empty space in between. So we will have much more higher core material, and this is also increasing the saturation level.
Okay, and then the next one, please discuss the AC losses in detail. What inductor specifications can be used to calculate reduction in efficiency due to AC losses?
Let me think. Because we have several specifications, we have the rated current is not related to the AC losses. We have the saturation current. Is also not related to, regarding AC losses, you don't see anything in the datasheet. You just can see, in case of MPS, not everyone is showing this chart. We are displaying the ACR versus frequency. in the chart, and there is a point you can see how much impedance or how it is increasing the losses. But in general, you cannot see if you are having, depends on the frequency you are using or you are in the system. If the frequency is regular levels, let's say 200 to 500 kilohertz, the losses is not high. But if you want to know in detail how are these ACR losses, these copper ACR losses, you can search in Google. There are some charts, and the charts, they describe at what frequency are increasing these losses, this proximity and skin effect. When is this increasing? They are very less at lower frequencies, but with increasing frequency is getting more. But it's something you cannot read in the datasheet. You can just see on the charts to have an idea in what direction is going.
All right, and sorry, Sven, I didn't make a note of when this one came in, but magnetic shielded is related to emissions? What's the question?
Yes, so when we have this kind of magnetic shielding, like in the semi-shielded inductors, it's not going to be like 100% shielded. Like in this case, this is not, in this case, this is the, from between drum core shielding ring type and molded type. These are the strongest shielded inductors. Then this is the non-shielded inductors, and the semi-shielded will be something between. Something between as emission. So it's going to be magnetically shielded, but it's not 100% like a shielding ring inductor.
Great. Next up, for the inductor measurement comparisons, did you actually measure the actual parameters like RDC, or was it based on the specification?
We're using with efficiency, it's comparing the whole device with the input voltage, output voltage of the currents, and we are driving by the frequency at several points from 0 to 3.5 amperes in this case. And in overall, we're measuring certain points from efficiency when loading, when putting some currents, and that are the results. This is not really based on our RDC. It's based on RDC, or copper losses, and core material losses. It's the complete losses in general.
Okay, and then also on this slide, there was a question of what happened to the third C inductor?
Oh yeah. I think I missed to put that curve. So I think it's my bad, but I think if you see already, it's tending to be very low. So I don't expect to have this a turnover having a very big performance. Yeah.
All right, so we got that one, and we have a second one on that one. So
I think it's.
I guess next time, make sure you keep your curves in there.
Yeah.
Okay, and then why does the start of the winding improve performance?
This is depends when. Let me open the slide, and I think it's this one. And this is when you have the start of winding. So this indication in the marking. This indication is telling us where is the first layer going. So it's going first layer up, and then a second layer and down, and so on. And the first layer is close to the core, and then it's coming a second layer covering this first layer. This is having a shielding effect, an additional shielding effect. And this is avoiding this audible noise. And it's also having an impact on the emissions. caused by the inductor. But depends how are you placing the startup winding. So if you place the startup winding close to the switching node, it's having better performance, or less emissions. So less emission, less losses.
Okay, thank you. How do proximity losses compare using a flat wire inductor and a rounded wire inductor for low voltage and high current output designs?
How proximity losses comparing? I am not 100% sure how to answer this. I don't want to lie to you, but I think having flat wire construction it's regarding the geometry of the wire. So you will have higher cross-sectional area, and when you have cross-sectional area that is higher, you have more cross-sectional area where the current can flow, and this effect is happening in the same way as in the round wire. So this is affecting the same amount, so depending of the frequency. So I will be expecting less AC losses when we have flat wire construction in the inductor, just by thinking on the geometry, because you have bigger surface. And this effect, proximity and skin effect, is reducing actually the cross-sectional area, but it's not having more when the area is bigger, is not also bigger, it's depending on the frequency.
Thank you. Next up, when is a shielded inductor recommended? Is it based on current, frequency, or other factors?
Shielded, when is a shielded inductor recommended? A shielded inductor is recommended when you want to reduce the emissions. When you see the different kind of components here, one point is to reduce the emissions of the inductor. The other point is, what is your priority? So you need how is the design? The design is cost sensitive. In that case, you can go on this kind of trump core inductors to reduce the emissions. If you want to have more or higher efficiency and have also some reduction of emissions, you can go for molded type. And depending of the material you are using, you will have also different core losses. Ferrite powder materials are having from nature low core losses. But if you are going for higher frequency, maybe it's better to use these kind of components. So it's it's a matter for really many parameters. Depends also on the temperature. They will have better thermal performance, the molded inductors, than the drum core types.
Great, thank you. Next up, you got to thank you for having a great session. And then, how important is inductor losses performance when it comes to EV?
Evaluation, probably evaluation. How important is the losses performance? As you can see here, so I'm really comparing. This chart is really with same size of components, and they're having really very similar. Maybe MPS is having 24. I measure against 20, I think it's 22 something, and the highest was 26. So it's very similar. You see the RDC losses are not very far away from each other, from the components I measure. And you see that at the end, because one or two milliohm is not making the difference. Maybe it's just every vendor have a, let's say, a recipe. How is this, in this case, this inductor recipe? How much turns, how much magnetic material, how much binding material, how much coating, and the whole component is making the difference. Mostly of the difference is making the core material itself. Having high permeability or less or good loss core material, it's helping here to having better performance.
All right, and then they want to know, where can we buy these inductors?
You can buy these inductors from MPS website. What is one option? We have also, if you need low quantities, you can go and check on the website, MPS website. You can buy by CODICO, for example. CODICO is having all parts in portfolio and can support you with the designs as well. Or if you need very small quantities, I recommend also for testing and try some catalog distribution like DigiKey Mouser.
All right, and then let's see. When calculating switching regulator efficiency estimate, it is easy to model the DC losses of an inductor because it is related to the RDC and the inductor current. But calculating the AC losses is hard because it involves parameters that are not very well known or shown in a data sheet. Any recommendations on how to model AC losses to calculate switching regulator efficiency in a simpler manner?
I know it's very difficult to measure the AC losses. So the core losses, it's very difficult to measure or to calculate. And if we calculate at the end on the real system, the numbers are going to be different. That's why my recommendation is to have a comparison like I did in this case, because there is where you see under your specification, under your device, and using exactly the same setup as I did, you can see the difference of performance from each vendor. You don't see this on RDC. Of course, RDC is making a difference, but if the RDC is too big, it's the difference is much higher than the inductor you want to compare. Of course, it's going to be reflected here as well. But if they are very close to each other, I recommend to have this kind of comparison.
Okay, and then they're asking for a clarification. Why is the rated current increasing with the rise in temperature?
Okay, the rated current, let me go one back. The rated current, it's related to the copper resistivity. When current is flowing through the wire is getting, it's getting hot. It's carrying some heat and it's dissipating some heat. Rated current, why it's getting hot? It's because when we put this rated current, what we have on the datasheet flowing through the inductor, let's have an example. When we have an inductor and the rated current is given, and it's one ampere. Let's say we will have, and we say that in the datasheet the specification is 1 ampere at 40K self-heating. So when we put this 1 ampere in the inductor, flowing through the inductor, we will have a temperature increase from 40K, and that's the meaning of having a rated current. And that's the meaning in this case. It's exactly the same. So when we put some current, so the rated current, what you see in the datasheet, some vendors, they have this value by 20, some of the 40. There are some of them by 35. So it's not really a standard. what is making so difficult at the end to compare the inductors. But if you understand how to read this value from the curve, it's helping you a lot how to to compare then really exactly the same parameters on their same specification. And it is when you have the rated current, you just need to go and search where is 40 or 30K or whatever you want to compare. And then you go just to, if you have 35, you go to that point. And from that point, you go back, you go down and you see the rated current by 35 is, in this case, from the chart is 20 amps. So it's related to the copper heat that is dissipated when flowing current through it.
All right, next up, can you comment on typical design techniques or applications similar to using the SOW trick? Are there other typical design tricks that MPS has seen, whether using switching circuits, filtering circuits, or other typical inductor applications and circuits that are seen in the industry? Any other specs that are engineered into your MPS products that we should keep an eye on as engineers and designers?
Well, there are some. I saw recently a very good webinar. This is at MPS webinar list. If I remember well, this is called, it's regarding the start of winding. How the emissions are if we have different scenarios, if we have this kind of PCB, the thickness of the PCB, if there is a layer of this material under the inductor, and this is called EMC webinar Inductors layout. I recommend to check that one. It's a very wide topic, but the webinar is very good, well done, and you can find more, really lot of tricks regarding the start of winding and how much it's improving the losses, the radiated losses from the inductor when having these different scenarios.
And Sven, this was one of the ones that we did?
Yes. This is at mps.com on their
Right.
webinar list.
So again, yeah, if you just go to monolithicpower.com/webinars, you should be able to see all of them on demand.
You can type also on the search field for webinar EMC inductor and you will find it.
Great. Let's see, for the efficiency curve, it says 500 kilohertz. This curve will change with, this curve will change with switching frequency. How do we account for that?
Yes, as you can see here, we are measuring at, the whole chart is by 400 kilohertz. What is changing here is the current. But the permeability, it's frequency dependent. And all core materials, what we have in the market, are frequency dependent. So that there is no other way. They are driven by the frequency and the losses are increasing by the frequency. In this case, normally all vendors are measuring efficiency at 250 up to 600 kilohertz. And this is because normally all converters, or the most common converters, frequency are in this frequency range. But if you are going higher on the frequency, you should be expecting lower overall efficiency. And this is not only regarding the inductor, we have also the IC. We have two components that are having high losses, and both are driven by the frequency. In this case, you can just expect a decrease of the losses, and it's driven by the frequency. This is the permeability of the inductor. It's the one that it's making that losses.
Next up, does the data sheet provide hysteresis losses?
No, it's not giving there. So there is no information related to the core losses. There is no way. It's difficult also to show in the datasheet. I think no one is showing this because it's very difficult, because you don't have this losses is regarding core material. And if you have just the core material in a toroidal ring core, it's difficult to, when you put together, how to describe these losses. And as we are selling a whole component, so with wire wounded inductor, so there is difficult to show this information in the datasheet.
Very good. And then you stated a lead time of 20 weeks. Are your parts under allocation?
No, we don't have we have certain amount of stock, of course, in the China and our MPS China warehouse. And so as we work very close with the colleagues regarding ICs and so on, we are having a very good planning regarding the inductors and the manufacturing. And that's why we are able to have this small I mean, it's not normal to have 20 weeks lead time these days, but yeah, we are able to do that. We have not the stock in the moment, but when we get the order, we immediately get in contact to get everything moved to get these parts in that lead time.
All right. And then how is inductor parasitic capacitance controlled?
It's not controlled. It's not really controlled. This is, I mean, we have, of course, we are trying to have very tight windings of the inductor, and this is because we don't want to have a higher resistance. So we need to reduce the resistance, and this is just you can reach by having a efficient winding of the core. But we don't have any measurement or control at the production regarding the capacitance between the windings.
All right. And then looks like we had a few come in via the chat, so I'm going to switch over to that. What is the maximum working voltage of MPS inductors?
The maximum depends of the size and the series, but we have up to 60, 80 volts.
Okay, and then is it possible? Whoops, sorry. Is it possible to modify the package of the power inductor such that it reduces the EMI due to the current being chopped?
No, we are not able to customize inductors. We just have the catalog components, and if we customize, this is increasing also the cost. But we don't have this, we are not offering this service. So we are just having these standard components in the portfolio without customizing or having customized options.
Okay, and then this inductor, can it be used for two-phase or is it only for single phase?
Just single phase. I mean, we have for DC-DC converters inductors, taking in consideration the voltage, the maximum voltage rating, which is 60, or depending of the size, 60 to 80. And yeah.
All right, and then next up we had, to reduce the parasitic capacitance in layout, can you cut out the local ground plane under the inductor without risking significantly higher chances of radiated emissions.
Yes, and this is exactly what is spoken in that webinar. When you look at MPS website for EMC, I think it's MC layout, Inductor, layout, Inductor tricks, EMC. You have exactly this kind of scenarios, and I remember because I saw it recently. I really highly recommend to go there and check that webinar from MPS, from monolithicpower.com. I think you will have exactly these questions or these answers and more tips for design layout. So I will search for design layout inductors EMC.
Yeah, I was trying to do a quick look, but too much going on here. So so I'm going to move on to the next question. Do you have any plans to offer, is that LITZ wire, LITZ-wire inductors?
No, not now. For now, we have just really round wire and flat wire, and LITZ wire. It's not in planning right now. It's not disclosed. It's not. We don't have plans for the moment.
All right. I think that is the end of the questions. Lots of questions today, Sven, but lots of good points to clarify on. That was really good.
In any case, if you have additional questions or you want to get in contact, you can always send or drop an email with your specific questions or doubts to powermagnetics@monolithicpower.com. You can find the Power Inductors website on their products Inductors, and there is the selector tool as well. And we have a very good overview, 2 slides flyer. This is also on the monolithicpower.com when you click on support and then product literature.
All right. And with that, I'll thank everyone for their time today. We will send out links to the on-demand video and the presentation in the next few days, and we hope to see you in our future webinars. Bye, everyone.
Thank you. Bye-bye.
Thanks. Bye-bye.